Hi, Jeff Lawton here. I want to talk to you about weeds. Plants in a wrong place, they say. Well, are they? Or are they just a response? Are they just a symptom and not a cause of a problem? If we look carefully and observe where weeds fit in to a reparative sequence, we can read the landscape. We can rebuild ecosystems by speeding up that sequence, moving it forward in time, and we end up in an abundant, productive system simply by understanding weeds without prejudice, without assumption, but just pure observation of the facts that weeds are some of our best friends. Here we have a classic case of compaction, and in this case it's ducks, an oversupply of ducks. And in any square metre of ground there can be thousands of different types of seeds that could germinate, but the germination condition determines what does germinate. And when you get compaction, you get decompaction weeds that germinate, dandelions in lawns. In this case, it's this Australian weed called Paddy's lucerne. And it's a decompactor. It has long tap roots. So if you compact, the opposite effect happens. You get a decompaction root germination weed. Now this is a really wiry little plant. It's pretty tough. It puts its roots down. Nature's in no hurry. It can wait for this plant to die, and these long decompacting roots die in the ground and create compost corridors that decompact the soil. Now, we could cut these off so that happens faster, or we could spike the ground and relieve the compaction. Either way, we know from this indicator that we've had ducks on the ground too long and they've caused compaction. It's the same with any animal or any vehicle. You get the same response from the decompaction weeds wherever you live. And that's just a matter of reading the landscape through the weeds. Another germination condition is when the soil is too loose. This little blue flowering weed here is a good variety of hairnet root. It creates a hairnet that actually holds together the soil. So this is a germination condition, the opposite to compaction. This is a soil stabilizing element. And if we carefully pull it up, you'll see the whole thing is hairnet. There's soil being held together at the surface. Now, it's not compacted, it's too loose. It's vulnerable to erosion. So the type of weeds that germinate in this condition function as loose soil traps, holding together the soil for stability's sake. Once it becomes stable, once this mulches down as the weeds go through their life cycles, then the soil gets stable, it's bonded together with organic matter, and it goes on to the next cycle. These are the things we have to understand. Here we have a classic bracken fern. Now, bracken ferns harvest potassium, and potassium, K on the element scale, burns off in a fire. You get potassium through all green material. When we have a hot fire, most of the potassium goes up in smoke as the green material burns off. A little bit is left as fine ash, but that very quickly leaches, leaving the ground depleted in potassium. Now, the plants that germinate then are specific specialists that can harvest potassium where it's in very short demand. And the classic worldwide is the bracken fern. It has a fibrous root and it's a classic harvester of potassium. If you analyze the bodies of these ferns, wherever they appear in any of the climates, you can guarantee that they're high in potassium, and if they're growing, there has been a fire. And that fire has left the ground depleted in potassium. Now, if you cut these and mulch them to the ground, they will reduce the germination of bracken itself. So if you cut a patch of bracken and slash it and mulch it to the ground, it will reduce by 1 meter. If you burn it and turn it into ash, you'll deplete more potassium and it will spread by 1 meter. These ferns are spread by fire, depleting potassium, and as they return potassium to the soil, they deplete and become more or less unemployed. Their job's done. Their function is to replace the depletion through the fire. So this is a sequence you can read all the way through the forests of the world, where we are destroying forests and ravaging the landscape with fire. So it's a very useful, life-saving way of reading the landscape. One of the classic weed functions of the world is to repair the soil when it's depleted of fertility with its base element nitrogen. And this is done by the peas and bean family, and right up through the same family within the trees. This is how landscape is repaired right through to the forest. This is a classic legume tree leaf pattern here. And here's another one. There are many types of leaf patterns, but these plants have a special ability to partner with a microorganism, a rhizobium bacterial colony in the soil, and they all have different rhizobium bacterial colonies. This plant here has nitrogen nodules at the surface where its roots are poking out, and these tiny little nodules are a colony of organisms that are fed by the plant. The plant's fast carbon pathways brings in photosynthesis and feeds these organisms with starch. In return, the plant is given nitrogen, and that quickly relates to protein. So most of the really good forages and feeds are also high in nitrogen because they're in that pea and bean family that have the ability to transfer nitrogen into the soil. Now this is a great way to fertilize the ground, and it's the way nature recovers. So right around the world, you can use this classic weed example as an indicator that the land needs to be repaired and the land needs to be given back for what you take. And that is why traditional farmers partner with nitrogen fixing plants. In a crop garden, where we want production coming out all the time, we know we've got to keep feeding the soil. We know at times we're going to exhaust the soil. We're going to bring in compost, we're going to bring in organic fertilizer. But we're in a spatial race with the weeds, especially around the footpaths and the edges. So if you replace the weeds with a designer weed, with a cover crop, a plant that fixes nitrogen, it takes up all the space. There's hardly any room for weeds. And these plants fix nitrogen. There's nitrogen nodules here. So there's nitrogen going in the soil, and the top of the plant here, that can go down as mulch. So we've got green manure mulch, we've got nitrogen in the soil, we're leaving structural roots there. It's got to be a better deal than trying to work with unruly weeds, difficult weeds. Design your own weed system, beat them at their own game. So when we understand how weeds control the ground and develop sequences and change over time, we can design a sustainable world. We can work with those natural systems. We can harmonize with the ecologies that repair the earth and go through to permanence, and that permanence can be productive forever. So we can all enjoy the journey.